For the next example, it's a little bit different, and it's because we have a rational expression. So with the limit as x goes to infinity of 14x to the third plus 3x squared minus 2x, all divided by 21x cubed plus x squared plus 2x plus 1. And the key to this is to find the highest degree term, term in the denominator, and just divide each term by that. So right here is going to be the highest degree in the denominator. So what I'm going to do is I'm just going to go ahead and divide every single term by that. So just give me 1 second here. Let me write this out, and you'll see what's going to happen here. So 14x cubed over x cubed plus 3x to the second over x cubed minus 2x over x cubed, all divided by 21x cubed over x cubed plus x to the second over x cubed plus 2x over x cubed plus 1 over x cubed again. That's too many x cubes. I never want to say an x cubed again, but I don't think I have a choice. Now, I'm going to simplify. Watch what happens in the numerator. I get 14 plus 3 over x to the second, x to the first, minus 2 over x to the second, all over 21 plus 1 over x plus 2 over x to the second plus 1 over x to the third. Now, if we think about this, what's really happening is, if we were to substitute in our limit, we're going to get 14 plus 3 over infinity minus basically 2 over infinity, because infinity squared is just infinity again. All over 21 plus 1 over infinity plus 2 over infinity plus 1 over infinity again. Now, if you think about this, 3 divided by infinity is nothing more than just 0. It's like having 1 divided by an extremely large number. So, all the highlighted terms, right here, here, and all 3 of these in my denominator are all going to go to 0. Because it's basically a constant divided by an extremely large number. So when you have that, what you're left over with is going to be 14 over 21, which is 2/3. So the limit as x approaches infinity of 14x to the third plus 2x squared minus 2x, all divided by 21x to the third plus x squared plus 2x plus 1, is 2/3. Okay? The next example, we're going to approach it the same exact way. So the limit as x goes to infinity of 9x to the third plus x squared minus 5 all over 3x to the fourth plus 4x squared. Now, when we approach this, we're going to do it the same way. We're going to look for the highest degree term in the denominator. It's going to be right here. I'm going to go ahead and divide every single term by that. So just let me write this out real fast. All right, so there's my numerator. Now my denominator is going to be 3x to the fourth over x to the fourth plus 4x squared over x to the fourth. I'm going to go ahead and simplify. That's going to give me 9 over x plus 1 over x squared minus 5 over x to the fourth all over 3 plus 4 over x to the second. And once again, once I substitute in infinity, let me just go ahead and do this real fast. We can see that in the numerator, the first term goes to 0, the second term goes to 0, the third term goes to 0. So I'm left over with 0 in that numerator. In the denominator, 4 divided by infinity is 0, so that's the only term. So I'm left over with 0 divided by 3, which is 0. Okay? So the last example, same approach. And the 3 examples I picked are very specific. There's a reason why I picked the ones that I did. Okay? So here's our last example here. So we have the limit as x goes to infinity of 3x to the second plus 3x all over x plus 1. Now I look for the highest degree in my denominator. That's right here. It's x to the first. So my approach is still the same. Write that out a little cleaner. Here we go. So I get 3x squared over x plus 3x over x all over x plus 1. When I go to simplify, I get the limit as x approaches infinity of 3x plus 3 all over 1 plus 1, which gives me the limit as x approaches infinity of 3x plus 3 all over 2. Now, if I were to substitute in my limit, really what's happening here is I have 3 times infinity, which is infinity. Infinity plus 3 is still infinity. And infinity divided by 2 is still infinity because it just keeps getting larger and larger and larger. So this goes to infinity. All right? Now, if we take a step back and look at what we have, I'm going to show you something that maybe you saw, maybe you didn't. I'm going to write the 3 examples that we just did. So the first example was the limit as x approaches infinity of 14x to the third plus 3x squared minus 2x all over 21x to the third plus x squared plus 2x plus 1. There's the first example. That equaled 14 over 21, which turned out to be 2/3. The second example was the limit as x approaches infinity of 9x to the third plus x squared minus 5 all over 3x to the fourth plus 4x squared. That turned out to be 0. And then the last example, 3x to the second plus 3x all over x plus 1, and that turned out to be infinity. So, like I said, I don't know if you saw this or not, but I'm going to give you a little, it's not a trick, it's just understanding the end behavior and identifying what you have. In every single example, we have rational functions or rational expressions. All right, polynomial in the numerator, polynomial in the denominator. Earlier, we learned about what polynomials do and their end behavior and everything. If I were just to take a step back and look, I want you to see something in the first example. Sorry, I don't know why that popped up. There we go. So in the first example, the exponents in the numerator and denominator of the highest degree are the same. When that occurs, your limit is only going to be the coefficients of those terms. So 14 over 21 turned out to be 2/3. That only happens, like I said, when your degree of the numerator equals the degree of your denominator. Okay? That means your limit is going to equal a over b, where it's the leading coefficients of those leading terms. Okay? Now, for the second example, I'm going to use a different highlighting color now. Here's the highest degree here. Here's the highest degree there. What ends up happening here is that if your degree of the numerator is less than your degree of your denominator, your limit is always going to equal 0. Always. Because what's going to end up happening here is that the numerator is going to get large, but the denominator gets larger much faster. So this is going to determine the behavior. Because that 3x to the fourth is going to overrule x to the third every single time. Now, with the last example, there's your highest degree here. Here's your highest degree here. And notice with this third example, your degree of the numerator is larger than the degree of the denominator. So when that happens, your limit will go to infinity, always. And it's because x to the second beats x to the first every single time. Okay? Now, I do want to do one more example, because this last example, excuse me, we do have to be a little bit careful about. Okay? I mean, it's just one of those things where you got to pay attention to what's happening. So here's our last example here. We're going to take the limit as x goes to infinity of 15 x to the second plus 3x plus 1 all over the square root of 9x to the fourth plus x to the third. Now, our approach is still the same. We're going to look for the highest degree in the denominator. And that degree, currently, if you just look at it, it's right there. It's x to the fourth. However, since that is contained inside of the square root, we need to be careful about what we divide everything by. So what I'm going to do is this. Inside the radical, I'm going to divide everything by x to the fourth. However, outside of the radical, I'm going to divide everything by that little simplification that I just made. The square root of x to the fourth is x squared. So outside the denominator, I'm going to divide everything by x squared. Once again, I just go ahead and do my simplifying here. So that gives me 15 plus 3 over x plus 1 over x squared. And then inside the radical, I'm going to have 9 plus 1 over x. Now, I'm going to go ahead and make my substitution. This is going to give me 15 plus 3 over infinity plus 1 over infinity over the square root of 9 plus 1 over infinity. From here, we're going to have 15 in the numerator. We know 3 over infinity is 0, 1 over infinity is 0. And then inside the radical, I'm just going to have the square root of 9 because 1 over infinity also goes to 0. So this turns out to be 15 over 3 when you simplify the square root of 9, which equals 5. Okay? Those are all the examples that I wanted to go over. In the next video, we're going to talk about finding horizontal asymptotes. Very easy to do. So I will see you in the next one.